Now, let's go ahead and just review real quickly what we covered last time, all right? And that is, we started talking about how we came with the catapult. And just like engineering today, you start at one spot and you may end up somewhere else. That's why, as you build things, make sure you document the process. Sometimes the process is much better than the final product because you can see how far you've come. Okay? Now, right now, you've got a bowman. They started out with bows and arrows, and they reinforced the bows and arrows. And then what happened is people could pull them, and they started breaking them. So they reinforced the bow and arrow. Well, it got to the point they couldn't break the bow and arrow anymore. And to make them more powerful, they get them tauter and tauter and more powerful. Then they couldn't pull them back, right? So after a while, they started developing like ballistas, where we used a machine and simple machines. Like there's part of the crank right there. All right? And so here's the history of it. So you can only store so much. So there is with the bows. Now I'll pull it up a little bit farther. All right. Now, so there it is, the reinforced bow, right? And it made it so, and this is bone of the animal, this is wood, and this is sinew. It's used in tendons, connective tissue. Then we went ahead and made, you can make this at home out of the plastic rulers and materials, different things. But what starts happening is our own bodies start limiting the weapons. So, and that's the length of the archer's arms, your arm and chest, strength and dexterity of fingers. And oh, by the way, we want you to do this while you're on horseback, which is pretty hard to do. So the best bows had about a 45 pull, and you could pull at 28 inches. All right. But you do a lot. I mean, the Mongols took over a great swath of this world, being just on horseback and arrows. All right. So here we go. And we learned as you increase that, it got greater. The more you increased it, the final little bit gave you a lot more stored energy. So then we started the belly buster bad boy here. And it could give you 3 or 4 times the draw force. So it could really be an impressive weapon. Then we had, so that's how you pulled it. And then you had the big arrow. So this way you didn't use your arms as much as you used your belly to help you push it down. And then you could launch it. And then we kept making them bigger. Well, after a while, you start making a stand, right? Using these ratchets to pull them back and forth, and you might fire 2 arrows at one time. And you're using wheel and axle here, right? There's the wheel, here's the axle. There it goes. Then what? We'll go ahead and we'll just jump on. All right. Then we start making catapults right here. All right. And what we do on the catapults is now we're using torsion. We're twisting the ropes and we're making them much stronger. We're building it up because we can use simple machines to help use mechanical advantage with simple machines and get you set there. Well, we're twisting. And, we looked at this bow, but we're going to go ahead and go on from that. So they started shooting arrows 200 yards with the ballistas. And then after a while, they realized, well, what we're doing is storing a bunch of energy, right? A bunch of energy into these stones. And then we're going to toss them 400 yards. It doesn't have to be sharp anymore. The massive power of that stone dropping on a building would just break it apart. All right? And they started putting these devices all in these castles, which made it pretty tough to get through. All right. And just a side note, you make these huge advances during military. Yes, that's true, but all it is will. If we really advance, let's go ahead. And remember, if you use math, as a tool, you can predict things. So you know before you even launch the arrow how far that arrow will go. You can use the math to start looking at speeding up the process in which you design things. All right, and we got the Scorpion and these others, just improvements on that basic trebuchet design. Then it got so big, we went to catapults, where you have an actual bucket. You can light things up, you can do all kinds of things. Same deal though, it's a torsion bundle, you twist it super tight. And you saw that when you made yours, all right? So there was a sling, and they called it an onager, and you would tighten that up, and you'd pull it. This piece of wood here, or this pillow-like thing there, was to protect it, so when it came up, it hit that and didn't break the wood. All right? There it is. Now, let's go ahead, and we did that catapult. Is there any questions about catapults with everybody right now? All right, then, what I'm going to do is give me 1 second here, and we're going to switch over to trebuchets, because those are pretty cool. Okay, so now let's talk about trebuchets. So we talked about, catapults, and we said they were in 3 categories, right? Ballista, traditional catapult that we think of, ballista, where it shoots a big arrow, and then trebuchets. We're going to start talking about the differences. A trebuchet launches a projectile from a sling on a pivoting beam. We put this on, before we were using just tension. Now we're going to put a weight on a box, and we can really hurl it. All right, remember the first catapults were designed by the Greeks and Romans. Those are 4 centuries before Christ. And about the same time, the Chinese were coming out with something called a trebuchet. All right. And we're going to be focusing on counterweight trebuchets. This really became the nuclear weapon of their time, the really powerful weapon. All right, were trebuchets. Okay. All right. And then again, Islam and different furthers, the Chinese and then the Islam and Byzantine Emperor kept improving this. Give the Middle East, they invented zeros. They were some of the most educated people on earth at one time. When Charlemagne defeats Islam from invading France, the people in the Byzantine part of Eastern Europe, which used to be part of the Roman, part of the Roman Empire that was in Western Europe and Eastern Europe, they could quote Greek and Latin, and Charlemagne, the king of France, was barely literate enough to write his own name. So I'm sure we came across in Western side as heathens. All right. So what happens is this counterweight, that's the weight right here. Everybody take a look. Falls this way, causing the other arm to spin over, releasing this. Now, for this to work, you have to have several things happening at once. But when it works, it's super effective. You could take down a castle. Trebuchets and gunpowder are the reasons why people stop defending castles. All right? All right, and we can go ahead, the physics of trebuchets here in a minute, but what I want you to see is here's the weight, and there is our mass. When we drop that mass down, this weight, though, what we're going to hit with, comes swinging up over the top. All right? This angle of this metal piece, really, this little tip there, really will impact how it does, too, by the way. And let me show you the site if you want to learn more about this. I'm going to copy it. Let me go ahead and put that here. All right. So there's a trebuchet right here these guys are doing, which is cool. Look at the weight of that. There's their bucket. They're going to be adjusting it. They call it Black Mamba. There's trebuchet. Wow. All right, let's go here. And watch how this trebuchet works right here, folks. that rock, the blue thing, is what you're throwing. But we put all our weight in here. Because of that and lengthening this arm, we can throw huge. All right, and it's all about friction and reducing it. All right. Bear with me 1 second, folks. We've just got to make sure it's not another group. Bear with me 1 second. I'm sorry. Let's go ahead and get started. Let me show you my screen. We just had a little bit of a technical problem at another location, okay? Okay. We're all set now, guys. I'm sorry. Again, I apologize. Sometimes we get a call in. All right. All right, let me see if Jaden's got a question here. We'll go ahead and do it. Yes, Jaden.
How would the trebuchet like not tip over with all that weight?
Well, that's
and
a great.
How would they like transport it, like move it to different places?
Ah, super questions. I wish I had some of my seniors ask questions like that. Here's what's going on. They generally build it on site. They would go and find a forest and make it out of the lumber of the time. They would go and take, rumor has it, they would go to the churches, and a lot of churches had lead in their roofs because that's a real good way to protect the walls and things. And they just would take it. They would take any of the materials that was around the neighborhood. So if there was, even if it was a church, and if it had lead, they had lead in the church, they would just take it out of the church. And they would use that lead and any other rocks as the counterweight. And the reason it doesn't tip over is because of this balance. What's happening here is, think of it when you're with your, think when you're with the little brother or sister and you get on a teeter-totter. You sit close to this fulcrum, that balancing point, like we've learned about some machines, and your little sister or little brother sits way out here. So you balance each other. Same thing on this, if you look at it. It's balanced. That's why it doesn't tip over. All right? Does that make sense, Jaden?
Yeah.
All right, cool. Good question. That's how, in fact, Jaden, if you look at this drawing right here, you see it. Here's the pivot point. This weighs 10 kilos. It's 1 meter weight. This weighs 2 kilos, but it's 5 millimeters. 5 times far away. That ends up being the force's balance. Okay? All right, let's see if we have any. All right, I'm going to mute you there, Jane. Okay, great. All right, thank you for your patience, folks. Okay, now, so that gives you a sense of what they were doing with it. And what's really wild is if you see some of these guys, this thing will hurl. They're on a football field. We built a wooden one at my school, and the trebuchet on this kind of design right here. And it was probably a 5 feet tall, all things considered, 4.5 feet. And you launched a golf ball. When you would launch it, it sounded like a 22 going off, a small rifle that you shoot. I grew up around guns when I was a kid. It sounded like that. And we launched it. I think we launched it a total of 2 or 3 times that day, and I never let them launch it again because it was too dangerous. It would go across the field. I was worried if it hit a car, hit a student, it would kill you. Be like getting hit by like a bullet. How did they get the rope to release when it fires? Great question. When this goes over, there's a little hook on the end of that thing. I'm trying to slow this thing down. I don't think I'm getting any. Right here. See that little hook? That's a loop, so it just comes off at one end, comes undone, and the other one stays attached. So that's how they did it. Does that make sense? That's why sometimes it's hard to make these out of Legos because you've got to have that pin there, and the way you adjust that pin will allow it to go. All right. The counterweight drops. That's what it shows. Swing the arm with a sling. Okay. This starts an arc. See, again, one part's connected, one's just looped on there. So when it comes over the top of this arc, that loop can come off and the ball can go. All right? All right. Can you guess some of the main factors that affected Trebuchet's performance? Well, I'll go with some. What of these things do you think would make it fly faster? Would we want to add more or take away weight on the counterweight? How many people say add more weight? Raise your hand. All right, excellent. Many of you said add more weight. That'll make it go farther. Think if you made this distance, you know, the leverage on this, you make these farther, do you think it'll hurl it more? The answer is yes. Did you grease this thing right here? The angle of that little metal piece, those all impact this. So the counterweight mass, counterweight height, projectile mass, the sling length, the launch angle. Also, we found that wheels makes a big difference. Wheels improves it. It allows this motion to go longer. If you have wheels, this whole thing can slide. It'll make it go farther. All right. All right. I want you to go ahead and play with that and start hitting counterweights here. So let's go ahead and do this. All right. I'm going to send this to you so you can go to this link. All right. And what this does, you can start, the goal is to go 650 feet. We'll close that. And you can start changing things. Like there's the projectile's mass. All right, so I'll use the same gravity. That same thing is, wait, there's the, you look at the orange number, I'm now changing the launch angle. Over here left, you can see I'm changing the mass. It's getting bigger there. It's at 100 kilos, right? Make that a little bit. Here's the counterweight mass. So the mass, the projectile mass is what you're hurling. Here's the counterweight to power it. So say we go 100 there. And then we'll leave gravity alone. Don't mess with gravity. And the counterweight height, I'm going to make a little bit higher. And launch. So I got to 400 feet right off the bat. So I could do as well, what do I want to do to, got wind down to 0. I'm going to take my launch angle. I'm going to go a little bit lower. Let's see what that does. Oh, that didn't work. Let's do this angle. I'm thinking it was on the pin. All right, so you got to keep playing with it because I'm still not getting there. All right, can I get everybody to go ahead and do that? It's 6:57 now. Let's take, let's try it. Let's play with this for about 8 minutes. Okay? I'm going to go ahead. I'm going to pause the screen, guys. I'm going to kill the volume. I'll be right back. Okay? In about 7 minutes. I'm sitting here. I'm just going to check on that other location. All right. Well, I just wanted you to play it so you could see the different things that infect it. Now, what was better? If you wanted to go farther, do you want to make the projectile mass greater or less? What would you say, guys and gals? All right. I'm getting a lot of people saying less, and that's true. To a point. You want the projectile mass is what you're throwing. You want that to be less. But you also don't want it to be ever a feather because it gets so light, so little mass, it won't push itself through the air. So I'm going to move this back, counterweight back to 25. I'm going to make my counterweight mass is what I'm dropping. My counterweight height is 100. Let's see how that launch goes. Oh, see? And I almost got 650 on that last one, 549. So then I could also, well, I could make gravity, but in real life you can't change gravity. I'm going to take my launching a little bit farther up. Launch one more time. Did it! All right. And honestly, it doesn't change anything. Just to fix speed. The large Trebuchet stood 4 stories tall, weighed 30 tons at 250-pound rock, 300 yards. It was wiping everything out. There's a great video on Nova if you ever want to see it. And it's about trebuchets. All right. Let me go back over here. What's wrong one? Sorry, bear with me 1 second here. Can't believe I got that far over. All right, now. Basically powered by gravity, its force is equal to 4 times the counterweight. Let me put this over here. Of the counterweight's arm's length, okay? The sling acts as a secondary fulcrum. So they're both, there's a fulcrum in this thing, a balance point right here, and then the sling acts like another balance point right over there. All right? All right. And again, we talked about potential gravity. That's a combination of mass times gravity times height. And just think about it, you know. And, you know, you got weight and you got height. The higher it up, you know, you're going to hit it with a little more potential energy. If you took the flight class, we talk about that altitude is potential energy, airspeed of an airplane is kinetic energy. If that helps you. Okay. Now, energy stored. How high up you can raise this? Okay. And how much weight is in there? So they started with dirt, but they decided they wanted heavier. They could go farther. Okay. Let me see if there's more questions. All right. I think they were trying to make that no gravity. All right. It's powered by, but see, the trade-off usually on the gravity is when if you don't have any gravity, then the trebuchet is not going to be able to fall down very hard. You know, you're not getting much energy. All right, let's go back here. Well, we'll leave this. This is for high school. But gravitational energy stored by the hosted counterweight is translation into rotational kinetic energy of the sling arm. All we're trying to say is, folks, that big fancy word is the weight of this coming down results in energy of this getting tossed. All right. All right, and let me see if I can get you this. So here's your fulcrum. Here's the distance. And here's the weight forcing. So that follows this down. Let me go up and get this up here for you. All right, and there you go. Storm the castle. Here you start getting into more and more. And there it is. There's the trebuchet. You know, that's really what you want to see. You've got screwdrivers, a belly bowl, these things. You get more and more torsion. That. This is a step. These all use torsion to power them. That trebuchet, all right, uses a mass weight. Oh, I don't want to do that. Why did I just... Okay, let me go back up to trebuchet. Thank you. Oh, okay, we had that. Sorry. A sling release is when a certain angle alpha is reached. At this point, the ring connected to the sling slips off, and the projectile is launched. So if it's going over this out, you got this angle. So that's how much it's going to go over. It slips off, and there's your counterbalance. This finger that the ring, that's what this part up here is, that ring, and it goes around this finger. You can bend that, and you'll really see a difference in how it does just by changing the degrees. And this you've got a fulcrum here, but at this rope going back, I set up here, didn't make it very clear. It's this part right here, because that's a new fulcrum. Watch here. We'll go ahead and pause this for a second. I'm going to pause the record. This virtual trebuchet even gets more elaborate. I'm going to go ahead and copy and put it over here for you. Try it again. I agree, that's very big. For some reason, I'm having a heck of a time. Let's go here. I'll do it this way. There we go. I'll send this to all of you. So you can do things like you can change that. And so for example, here's this length of the short arm, length of the long arm, length of weight, height of pivot arm, uniform mass, all these things go in there. Submit it. There it is. How do you like that special sound effect? So let me show you where you go to change this stuff to play with this a little bit. Right here is the length of the short arm. And then let's look at the length of wood, half pivot, length of long arm. Make that 9. And then submit. So you really get you can see the distance and the height that you can get. So if I made that long arm 4, let's see, I went 259 feet. I'm gonna go ahead and submit that. Let's see what that did. 138 feet, so that didn't work so well. So you start to get a sense that here's 12 feet. I'm going to go the other way. So that went 166 feet. Well, let's try it now at 8 feet. And this went 276. So what you're going to see is there's a range in there that works, and then once you get outside of the range, it doesn't work so well. Another thing you can change, which I love about this bad boy, is you can change, well, there's the mass, inertia weight. Let's look, mass of weight, projectile, mass of weight. Let's go ahead and make this 200 pounds. Submit this now. Now we're at 388 feet. So let's spend a few minutes here. Go ahead and paying it around here, folks. And yeah, Jay, that last thing was huge. They were launching there at that place. I loved seeing the guys walking the hamsters in the video. Go ahead, everybody try this. Go up here and change these different things, and then kind of in your back of your head, play with it at the two ends of it, okay? In other words, what I would do is say, okay, I just added mass. Is there a point which the mass is into? Great. Oh, I got a baseball. What happens if I wanted to throw a pumpkin? There we go. Let's throw that bad boy. Pumpkins. But pumpkin guys do that. See, it only went this time 52 feet with that kind of pumpkin. So I need to do something. Let's make that 500 pounds. This is why almost all engineering is done with simulations first, so you can sit down and try out ideas to see, hey, would that work? Still only 191 feet. Let's try that pumpkin. Let's go to 1,000. What's great about this simulation, you don't have to worry about it breaking. I doubt that if you were putting 100 pounds in it, you wouldn't have designed it to handle 1,000. But there you go. Here it goes. Mr. Pumpkin's going. Finally got up to 387 feet. But look how much mass we needed to do that. All right? Any questions on this? Let's go ahead and net this. Next week, just to give you an idea, we're going to do architecture, kind of the ancients architecture a little bit, and then we're going to go into SketchUp. All right? And you'll start drawing architecture. And then we're going into 3D printing. Let's see if we got a hand here. Yeah, John. Hey, John.
I found this game on the internet.
Yeah?
It's called Besiege.
Oh, yeah.
It's really cool. It's like 3D, and you build your own siege weapon.
Yeah, I saw that. I actually wrote to him as a teacher to say, hey, what kind of price could I get us that? $6 a person. The problem is it's super bloody. There's,
Yeah, I saw that.
Yeah, that's where I was disappointed. I was like, could we just turn that down so I could have it in a classroom where, I can't,
I might get it for myself.
Well, for yourself, it might probably be a lot of fun. I'm going to be a little bit envious. Have you tried messing with this simulator yet?
I can't get the link to work.
Raise your hand. John, I'm going to put your hand down just for a second. Raise your hand if you got the link to work, guys and gals. Try it in Chrome if you didn't get it. I'm having luck. I'm running in Chrome. Try it in Chrome. If you didn't get it to work, try it running it in Chrome. What are you trying to run it in, John?
It's not really that it just won't open. It's just I can't click on it.
You can't click on it. So I send you that message. Just highlight it and copy it.
Yeah, I'm doing that now.
That's what I would suggest. Here, I'll put it this way too. Try it right here.
Okay, it worked.
There you go. Give it a try. It's fun. Plus, if you were going in a pumpkin throwing contest, I would definitely have a tool like this as I'm doing it. Let me see here. I'm going to go ahead and mute you.
Oh.
There you go. John's discovered it. He's a happy camper. Much happiness abounds. But, guys, really what we do in engineering anymore is you're really going to want to do, look at the velocity of what these things get going. You get the mass, we're making it bigger. We're kind of ignoring the mass of the arm and every other thing. Let's see what they have for a cow. Oh, same, I thought. You make a custom one. There's a baseball, golf ball. Watch to see when you submit a golf ball in this. Now you're 730 feet. That's 2 football fields in length. And you're getting an airspeed. What's the speed of that thing? 265 feet a second. That's hauling. Somebody have a question up here? Yeah, Aiden.
I have Besiege on my computer.
And what do you think of it?
It's pretty cool. I put a link to the website on Edmodo yesterday.
Okay. All right. I'll go back up and look at that. That's a little bit, like I said, a little violent, so we got to be careful on that. Let me ask you, is anybody entering in the contest? I'm going to go ahead and mute. Raise your hand. I'm going to mute you, Aiden. Raise your hand if you're going to enter in the contest. Excellent, guys. Let's get it raised in there. It'll be great times. All right. Make sure you get in. You got it next Monday. I just did. Let me see. Right now, I've had a distance of 734 feet because I've got no wind. Don't change the wind. Sling wasn't intention the whole time. I'm gonna go back and look at that. See who can get. See who can get the. Has anybody beat 734? All right, I got one. What is the? Let's see what the scores are. Write them down there. I'll start reading them out. Wow, one at 286. 288. Oh yeah, 2862. 2862. Go ahead, folks. See if you can beat that one. That's pretty far. Did you turn? You hope didn't turn gravity off. Can't turn gravity off either, guys. Or that should just really impact speed. I gotta be careful about that. Let's see if I can do this. I had 150 that way. Let me see something else. Well, that didn't help. That hurt it. All right, they got me to 1,000. All right. 1923. Wow. 1,059. 35 with the cow. 3542. John, you're the man. Jane, 3433. I kind of cheat, though. I was wondering what you were doing there. Pumpkin. All right. What are you doing to cheat? Or how are you gaming the system, shall we say? Yeah, you put the weight like stupid high. Like I got 1,000. In reality, you wouldn't be able to build it. I'm going to make this another. Yeah, I just got mine up to 1,600 doing that. I'm also making my projectile diameter very small, so there should be very little air friction there. Let's try that. Oh, well, let me do that because we said unless I do custom. Wow. I beat everybody. 7,000 feet. I got 7,000 feet. Look at my projectile. And you know what I did? I made the mass of the projectile very small, and I made its diameter small. So it went 1,500 feet per second. It was in the air 32 seconds, believe it or not. As always, you want to get faster in things, make it lighter. That's a lot. Yeah, I think I got you on that one, guys. And if you think about it, as long as it's dense enough, you can throw something small pretty far. You can throw a baseball farther than you can throw a softball. I still got, you got 12,000? Ah, you got me beat again. People are now setting all the different skies Ryan got. And that's with a try with a cow. Yeah, I've been doing that. Wish I had a little cow going through there. People, Chick-fil-A cows wouldn't like that, though. All right. Well, folks, that's what we have for this week. You don't have lab next week. I believe you got 3 weeks without labs. And turn in that offer. We'll do a little architecture, and then we're going to do some 1, 2, 3D SketchUp. Yeah, I'm sorry. Boo, too. I agree with you on that. And I hope you all have a great day. And I will talk to you this time, well, Monday of next week, okay? The files, make sure you go on YouTube. If you miss a class, make sure, and if people are missing the class, you need to tell them to come to these webinars. We're going to go back and do an attendance now. Make sure you're on YouTube. Check theirs where they can get the old webinars. I also sent Mr. Maurer PDFs of what we've been printing, okay? I will post this probably as soon as we get off this. I'm going to start recording it and uploading it to YouTube. Okay. Well, y'all take care. Bye-bye. Have a great day.